Greetings, everybody. So today we are going to discuss about the one shot of our new chapter, which is solids. Solids, basically, first and foremost, according to the kinetic molecular theory, solids are those, it is a state of matter. It is a state of matter which is having the lowest amount of kinetic energy, in which the molecules are tightly packed with each other in the in a regular geometrical manner. In a regular geometrical manner. Now, according to the kinetic molecular theory, there are certain properties of solids such that, as you can see in the diagram, gases basically had the characteristic that gases had molecules which were quite far apart from each other. No intermolecular force was present between them. Likewise, their kinetic energy was highest when it comes to liquid. Liquid basically had little gap between them, closely gapped, as well as they have close intermolecular attractions, due to which there were intermolecular gaps present between them. As a result of which their kinetic energy was moderate and somewhat restricted. But when it comes to solid basically do not have the the kinetic energy, completely independent. The kinetic energy is completely restricted in such a manner that the solids are having their kinetic energy all accompanied within a single you know geometrical shape, such that different solid particles do not have much kinetic energy, to which they have high intermolecular forces of attraction developed between them, as a result of which they are arranged in a geometrical manner. Let's study what our book says about it. So here, there are simple properties of solids related to interparticles association based on some limitations. So here, kinetic energy, as I previously told, that they do possess a very short amount of kinetic energy. Reason behind it is their high amount of intermolecular forces of attraction, which leads to a vibrational motion rather than translational or rotational kinetic energy. As in um, gases, we saw three types of motion. One was the, let's suppose if you're having a monoatomic gas here. Now, when monoatomic gas will be there, it will be following a translational motion. It will be having a translational motion because it is only made up of one atom, one molecule. So on the other side, when it comes to diatomic gas, let's suppose there's chlorine. Diatomic gas chlorine will possess a characteristic diatomic gas. Chlorine will possess the characteristics homodiatomic gas. Chlorine will possess a characteristic which would be of vibrational motion, which means it when the molecules will tend to move, and electrons will tend to move far apart, the force of attraction will attract the molecules together, due to which their kinetic energy will be restricted at that moment internally, not externally, as a result of which they will be having a vibrational motion. But when it comes to triatomic molecule, let's suppose we are having a hetero molecule CH4. In diatomic molecule we cannot consider hetero but homo molecules, right? So here we are having CH4. There's C carbon. Just trying to draw a rough structure. Here carbon is in middle, and here there are four hydrogen atoms. So these hydrogen atom will tend to move far apart from carbon, due to their kinetic energy will be attracted by the force of attraction, which is causing to attract the hydrogen towards the carbon, which is known as the van der Waals attractive force. Van der Waals attractive force. Now, it is basically a primary force of attraction. Uh, Apart from that, this is a primary force of attraction. Van der Waals primary force of attraction. And here the motion which would be accompanied would be a rotational motion, as a result of hybridization model. As a result of hybridization model, we knew that there was a carbon, as well as let's suppose carbon is having its hybridization value as what, sp3 hybridized orbitals, which means four sp3 hybridized orbitals are there, due to which one hybridized orbital would be on in four direction. Let's suppose here these are the four hybridized orbital, and now when they'll bond, they will be having this type of overlapping with each other with the hydrogen atom, due to which they will form a hybridized orbital, due to which there will be a motion generated between them, which would be a rotational motion. But when it comes to the solids, particularly solids only exhibit vibrational motion, such that whenever their molecules tend to move far apart from each other, they are attracted by the high intermolecular forces of attraction, as a result of which they tend to vibrate back and forth on their position. due to which they generate vibrational motion. Moreover, when it comes to the intermolecular forces, they have high intermolecular forces, which allows them to adhere tightly to a fixed position. Moreover, when it comes to compression, compression in solids is nearly incompressible. According to kinetic molecular theory, the particles are tightly bonded together due to the attractive forces, and small empty spaces are left among them. It makes a solid denser, rigid, and hard due to its non-compressible state, and it can withstand considerable external pressure. Moreover, when it comes to its diffusion, solids diffuse very slowly as compared to liquids and gases because they have close packing of particles, due to which their spreading out or a movement is restricted. Restriction of their free movement is there. Moreover, when it comes to expansion, solids can expand on heating, but this ability is very less as compared to liquids and gases. Moreover, these particles of solid are arranged orderly in a fixed position, such that an increase in temperature can cause their attractive forces to be weakened, and thus they can result in increase in the volume. But that increase in volume is only limited to a basis such that above that limit, the solids will tend to convert into their state of liquids if they are given further temperature, further heat. Melting solids melt on heating at a particular temperature, such that the vibrational energy of particle increases on heating until at melting temperature the vibrational energy of the solid particles overcome the energy of existing bonds. Otherwise, this is the limit which I was talking about. Moreover, sublimation is a process in which solids directly convert into gas without overcoming the state of liquid. So in this case, some solids directly change into vapors on heating without passing through liquid phase. This phenomena is known as sublimation. For example, naphthalene is a solid, as well as iodine are solids. These all are solids which are molecular solids. They are under the class of molecular solids, such that these molecular solids are having weak forces of attraction, which are known as the London dispersion forces. As a result of which, these London dispersion forces existed are the weakest bonding due to weakest secondary forces of attraction, due to which when they tend to hold the solids remain holded, and remain within their uh, region within the range remain within their range for a certain amount of time. But when they get immediately some sort of high amount of energy, they change their state directly from solid into gas. For example, solid carbon dioxide, dry ice, comfort. Comfort basically it is just like you know small what small tablets of iodine, which are small tablets of iodine gas. Iodine basically such that when we keep them somewhere in winter, then it remains cool down and within the given environment. But when it comes the summer season, and during the summer season, it tends to warm up and immediately convert into its gaseous state. So these are some things which I wanted to discuss. And here, the opposite of sublimation is deposition, in which gas is converted into solid. When it comes to types of solid, first we are having the you know a primary distribution of solids into two things. First includes crystalline solids, which are known as true solids, and second type is amorphous solids, which are known as pseudo solids. Pseudo solids, false solids, which are not which are having solid like characteristics, but in actual they do not have the necessary arrangement, necessary three-dimensional regular geometrical arrangement, which can classify them as solids. Now, crystalline solids are characterized by definite geometrical shape and sharp melting points. These are known as true solids. These solids in nature occur as crystalline solids. Examples of these include sodium chloride, diamond, graphite, sucrose, ferrous sulfate, and other examples are also there. When it comes to amorphous solids, they do not have a three-dimensional regular arrangement of particles, and these are known as amorphous solids. Pseudosolids, they do not have long range of order of particles and assume them closer to liquid, such that on continuous heating they gradually soft and convert into a flowing liquid. And uh, one more thing, that these basically are not having a fixed melting point, such that they do not have a fixed melting point. They can be melted at a range of temperature rather than a fixed temperature. Let's take example of glass. Basically it is not a solid, it is an amorphous solid, or in other words we can also call amorphous solids as a super cooled liquid. If we super cool liquid, first if we are supposed to um, if we are supposed to cool down a liquid at a very slow speed. If you're supposed to cool down a liquid slowly, then it will, tend to develop into a solid. But if you tend to if you're supposed to cool down a liquid at a high temperature, sorry, if we are supposed to cool down a liquid slowly, then it will be turned into a crystalline solid. But if you are supposed to cool down a liquid uh, you know at a very high rate, very fastly, so at that moment what actually happens is that the liquid molecules, the liquid atoms, the atoms of this particular liquid, the atoms of this particular liquid are not able to the atoms of this particular liquid are not able to uh, occupy or equip their 3D geometrical shapes, such that they are unable to occupy their geometrical arrangement whenever they are cooled fastly, such that when they lose their kinetic energy, the movement is the loss of kinetic energy is so fast that they are unable to get their regular 3D arrangement, as there's a sudden loss of kinetic energy, as a result of which instantly they will certainly and instantly they will ultimately converted into a pseudo solid without a proper arrangement. This is a mechanism behind it. Moreover, amorphous silica is one of the best. Let's read this as well. Amorphous silica is one of the best materials from converting sunlight into electricity, because it is a pseudo solid. So in that case, this is helpful. Moreover, when it comes to certain differences between both of them, differences between both of them are given such that crystalline solids exhibit geometrical shape, they have sharp melting point, they show anisotropic behavior. Now what is anisotropy? Anisotropy is a characteristic such that if you are having let's suppose graphite. Graphite is a crystalline solid and has a characteristic that in it can only conduct electricity perpendicular to its surface. It can only conduct electricity, in the vertical direction. It cannot conduct electricity in the horizontal direction, right? So it can only conduct electricity in the perpendicular surface, in vertical direction, not in horizontal direction. As a result of which, uh, this property of solids, which is associated with their directions, is known as anisotropic property. Such that some solids are having their properties specifically defined in a particular direction, such as conduction of electricity, conduction of heat, as well as the refractive index, which are dependent on the direction of the solid in which they are kept. So in this case, if we are going to utilize graphite basically does not conduct electricity in parallel direction. Sorry, it does not conduct electricity in the perpendicular direction, but it conducts in parallel direction. Let me just write it. It conducts in parallel direction, right? And likewise, if we talk about other compounds, it if we talk about the refractive index of graphite also has similar characteristic that uh, refractive index of graphite cannot be it has a refractive index when it comes to vertical direction. In vertical direction, it does have a refractive index because in vertical direction there is refraction occurring. But if we talk about the horizontal direction, there is no refraction occurring, due to which refractive index of graphite in horizontal direction would be zero. And reason behind it is something as let me just draw the structure a bit. Let's suppose these are the molecules of graphite. Just trying to draw a rough structure here. As we are having the molecules, right? So let's suppose light is coming from the horizontal direction. When light is coming from horizontal direction, so as the light ray is coming from the horizontal direction, so this light ray coming in the horizontal direction when will strike towards graphite. So in the horizontal direction, the graphite is having no intermolecular gaps or in the horizontal direction, such that in the horizontal direction there is no intermolecular gap present between their atoms, due to no intermolecular gap between their atoms and presence of matter in front of its path, the light ray will, instead of being refracted, will now be will now be reflected, such that it will reflect back from its path uh, in the opposite direction. But when it comes to light ray being passed in from upside, if it is coming from upper direction, so from the upper direction there is presence of some sort of there's presence of the intermolecular gap between the atoms, as a result of which when the light will tend to come from the upper direction, it will showcase that the upper direction has intermolecular gap between the atom, due to which the light is then able to pass through the intermolecular gaps partially, as a result of which it will be able to now refract instead of reflection, such that it will change its pathway, but it will be able to pass through the graphite in the vertical direction, as a result of which it will have a refractive index. It will have a refractive index in this direction, and it will not have a refractive index in the horizontal direction. So this is a basic concept, apart from which same goes for electrical conductivity, such that if we talk about electrical conductivity, if current is being passed, let me just explain it here. So uh, when it comes to current electrical conductivity can also be explained in this manner, that if you are having carbon in we know that in the structure of graphite we are having basically it is an allotrope of carbon. Graphite is an allotrope of carbon, and it is the most stable allotrope of carbon as well. Such that if we talk about its structure is arranged in such a manner that here we are having one carbon. This is a central carbon, and down towards it there is one carbon on this side, one carbon on this side, and one carbon on this side. This is the actual structure in which the graphite molecule is arranged. And on the top we are having a free electron of carbon from this side, right? So when the carbons are able to arrange in this side in this type of geometry, so whenever current is passed in the horizontal direction, in this direction, let's suppose current is passed in this direction, and here there is the positive terminal of the battery, negative terminal of the battery, and when current is able to pass in this direction, so in this direction there is no free electron present on the side of carbon, due to which current will not be able to be conducted on the horizontal side. But if the battery is connected into the vertical direction, if the battery is, let's suppose, connected in the vertical direction, then at that moment when it will be connected into a vertical direction there is a presence of free electron, and as there's presence of free electron in the vertical direction, it's due to the presence of free electron in the vertical direction, the graphite is then able to conduct electricity in this direction. So this is a concept behind it, that why does it actually occur. Now there's a similar mechanism occurring in terms of thermal conductivity, that's such that if we talk about thermal conductivity will have the same uh, process. If we talk about the conductivity in the horizontal direction, let me just try to, if you're providing heat in this direction, if you are providing heat in this direction, then in this direction we are having, in this direction, in the horizontal direction, the molecules are quite closely packed with each other. Molecules are closely packed with each other, such that all these molecules are having no intermolecular gaps, which means these are closely packed with each other. High intermolecular forces of attraction persist in the horizontal direction. So as there are high amount of intermolecular forces persisted within the horizontal direction, it is clear that we need to provide more amount of heat in the horizontal direction, which means thermal conductivity is more in horizontal direction. But when it comes to the vertical direction, in vertical direction there is presence of intermolecular gaps. These are the intermolecular gaps which are present over here, such that these intermolecular gaps indicate that there is less amount of intermolecular forces, less attractive forces are there due to more intermolecular gaps, as a result of which there is more intermolecular gaps, as a result of which we can decipher that due to less intermolecular gaps, due to more intermolecular gaps and less attractive forces, there will be requirement of less amount of heat energy, due to which there is less thermal conductivity in the vertical direction and more thermal conductivity in the horizontal direction. So this is what we call as a phenomenon known as anisotropy. Apart from which, when it comes to another concept, uh, we are also having another concept regarding it, which is known as isotropy. Isotropy is simply, properties which are not dependent on direction. So this is known as isotropy. After this, when it comes to uh, other characteristics, amorphous solids do not show anisotropy, hence they are isotropic in nature, and they can be cut down at fixed cleavage plane. Now, cleavage plane is also an isotropic behavior, such that if we are able to cut diamond, let's suppose this is diamond. I'm just roughly trying to make you assume it. So let's suppose if we are drawing the structure of diamond. So in the structure of diamond, we are able to cut diamond only at 45 degree. We can only cut diamond at a particular angle through a particular plane, which is known as the cleavage plane. At a particular angle, we are able to cut the diamond such that otherwise, if we are able to cut diamond, we won't be able to cut it at any other angle. We are only able to cut diamond at 45 degree. So at that moment, the plane at which we are able to cut the crystalline solids is known as cleavage plane. Now that cleavage plane is it is a fixed cleavage plane for crystalline solids. Crystalline solids can only be cut through a fixed cleavage plane, but when it comes to amorphous solids, they cannot be cut through a fixed cleavage plane. They require uh, they require other sort of cleavage plane. Have multiple directions in which they can be cut. Example of this is rubber. Rubber is not a crystalline solid, so rubber can be cut in many directions. Moreover, when it comes to diamond, as given example, 45 degree eh, is the point at which it can be cut. And one more thing, that here, uh, if we are supposed to cut glass, let's suppose glass is also an amorphous solid. First and foremost, glass is not having a cleavage plane, due to which we are not able to cut it in a particular direction. And another property of glass is that we can only cut glass with the help of a charcoal. We can only cut glass with the help of a coal, just like a black diamond or impure diamond which is present. But we can only cut glass with the help of that. There's also a reason behind that as well. Now coming to the properties of crystalline solid, such that crystalline solids, number one, here have the anisotropic properties, apart from which they have symmetry as well. If they are having geometrical shape, they must also possess a symmetry. What is symmetry? It is basically the property. It is in which when a crystal is rotated at a certain angle, when a crystal is rotated to a certain angle, there is a regular repetition of its edges and faces. Such that if we take the structure of a simple cube, cube is a geometrical shape, right? So here, let's take the structure of a cube, simple cube. Oops, cube. And here, as you can see, this is the structure of the cube, right? So this is the structure of cube. Now within that cube, the side which is forming this cube, let's suppose this blue side which is forming this cube is known as the edge of the cube. Here, while the points at which the two or more than two edges are combining together is known as corner. Whereas the front size, I mean the face of the cube, when the edges are combined together to form a single two-dimensional structure, this is known as the face of the cube, right? So whenever we are going to repeat the crystalline solids to a particular angle, then there would be a regular repetition of its shape, a regular repetition of its what do we call it, there will be a regular repetition of its shape, which would be known as the symmetry. Regular repetition of its edges and faces, which is known as symmetry. Now here there are some terms regarding symmetry, such that the first term is plane of symmetry. First includes plane, so that if there is an imaginary plane which divides the crystal into such a way that one part of that uh, one equal part of that uh, crystalline solid is the image of the other part, then that plane is known as the crystalline plane. As you can see in the diagram, that here we are having a plane of symmetry ABC. Here, as you can see, these represent the planes of symmetry. If we are cutting the crystalline solid in this direction, then it can give us a mirror image, an image of two equal parts which are exactly alike. Axis of symmetry, it is basically an imaginary line on which a crystal can be rotated through 360-degree. As you can see, there is axis of symmetry. If you're supposed to rotate it somewhat here in a 360-degree, then we'll be able to do so through this plane. So this axis is known as axis of rotatory, axis of symmetry. After that, when it comes to center of symmetry, it is a point in the crystal from which we can draw a line. This line intersects the surface of the crystal at equal distance on either side, such that this is a central uh, atom. Let's suppose this is a central point, center of symmetry, and from that center of symmetry, all other edges as well as all other corners, faces are at equal distance from each other. This is known as the center of symmetry, axis of symmetry, and plane of symmetry. Now there comes a term about two different types of cubes: face centered cube. There are two cubes, right? Let's suppose there are two major types of cubes, which includes primitive cube. Second is non-primitive cube. Primitive cube, non-primitive cube. Primitive cube is the one in which, if we are having, let's suppose, a crystalline shape. Now when we are going to draw that crystalline shape, all right, so this is a rough diagram, and here now a primitive cube is the one which is only having its atom located at the edges as well as the faces. The cube which is only having its atom located at the edges is known as the primitive cube, and the faces. But on the other side, sorry, primitive cube is the one which is having its atom which is located at the center as well as the edges and faces, whereas non-primitive cube is the one in which there is atom located in the edges, face and faces, but not in the center. So the non-primitive cube is the one which is not having the atom located at the center of the symmetry, but located at edges as well as faces as well as corners. So these are two common terminology. Now primitive cube and non-primitive cube. Here the non-primitive cube, which is having its atom not located in the center of symmetry, can be divided into three major types: face-centered cube, such that the atoms are located at the faces; edge-centered cube, ECC, atoms are located at the edge; and on the other hand side, there is body-centered cube. Face-centered cube located at faces, atoms located at faces; edge-centered cube located at edges; body-centered cube uh, located at the center of the body. So these are the classification of primitive and non-primitive cube. Now here, apart from that, we are having geometrical shape of crystals. We know that crystals possess a repetitive arrangement of three-dimensional shapes, so they possess a definite geometrical shape. We are going to discuss what type of geometrical shapes these are. There are the number of shapes among these geometrical shapes are around Around seven geometrical shapes are there, which we are going to discuss, and very important as well. And cleavage plane, sharp melting point already discussed, cleavage plane already discussed, and crystal growth. When a hot saturated solution of the salt, when a hot saturated solution of the salt of a molten solid is allowed to cool slowly, so at that moment the crystals grow in various direction, and this is known as crystal growth. For example, a slow cooling of the hot saturated solution of table salt can give us cubic crystals. One more thing, that during the crystal growth there is uh, the pattern in which the crystalline solid grows, and that pattern in which the crystalline solid grows is known as crystal habit. And crystal habit, for let's suppose using the same example, table salt has its crystal habit uh, when without any sort of impurity as cubic crystal. But if it is given 10% impurity of let's suppose urea, so at that moment its crystal growth will be different, such that instead of forming a cubic shape it will form another type of shape, which would be uh, you know uh, a bit of hexagonal, right? So in this case this can be the possibility. One more thing, that if we are doing the opposite of it, instead of cooling them slowly, cooling them fastly, cooling the crystal at fast speed, so at that moment when we are cooling them slowly, and there's development of a crystalline solid. If we are cooling them fastly, there will be development of amorphous solid. Anisotropy previously discussed. Likewise, if we talk about isomorphism, yes, it is an important topic, such that the phenomena in which different solid substances exist in the same crystalline shape is known as isomorphism. If we are having two or three different substances, two or three different shapes, which are having same crystalline structure, is known as isomorphism. Now, having same crystalline structure can only indicate that it is having the same atomic ratio, but in actual the physical as well as chemical properties for these isomorphic substances will remain different, sorry. So the physical and chemical properties will remain different, while the atomic ratio will be remaining same. Apart from which, when it comes to the name of these substances, these are known as isomorphous substances, and the behavior is known as isomorphous, right? Moreover, some examples are given in our books, that here sodium chloride and magnesium oxide, such that they are having their atomic ratio as 1:1, right? Such that they have 1:1 as the atomic ratio. And apart from that, when it comes to geometry of the unit cell, the geometry of the unit cell is cubic. We are going to discuss what is the characteristic of each and every geometric cell. And when it comes to sodium nitrate has and as isomorphic capability with calcium carbonate, such that it has a rhombohedral geometry there. Moreover, when it comes to zinc sulfate and nickel sulfate have an orthorhombic geometry. Moreover, silver sulfate and sodium sulfate have an hexagonal geometry, but it doesn't mean that they have they have same physical and chemical properties, or as there are different chemical and physical properties for them. When it comes to their other characteristic, unique feature of crystalline solid is that they have phenomena of exhibiting polymorphism, such that if we are having a single substance which can exhibit its crystalline structure in more than one shape, then it would be known as polymorphism. Such that we are having certain compounds such as calcite or aragonite, calcium carbonate, limestone, calcium carbonate, which can exhibit its two crystalline forms, which are known as the polymorphs of the calcium carbonate, which are known as calcite, which forms trigonal crystal structure, and aragonite, which forms orthorhombic crystal structure. Now they have same chemical composition, but their physical properties are different. Even though they have same chemical composition, their physical properties are different due to different arrangement of their atoms. Moreover, when it comes to some other topic, there's a difference between two things. First is polymorphism, second is allotrophy. Allotrophy is only for elements, which means atoms of same type. But when it comes to polymorphism is only for compounds, such that it is for atoms of different types and compounds ultimately. right? Moreover, when it comes to allotropy applies to pure elements only, such that the existence of same elements in two or more different crystal structures having the same chemical nature but different physical properties are known as the allotropy. Even though both of these are having the same chemical nature, same chemical properties are there in allotropy as well as polymorphism, different physical properties are there, but the difference comes that allotropy is limited to elements and polymorphism occurs in compounds. Now, carbon exists in more than two allotropic forms. Generally, there are four, which includes diamond, graphite, coal, and charcoal. Coal and charcoal are unstable forms. The one which we are going to discuss here is diamond and graphite. Diamond basically has a cubic geometry, while on the other side, graphite has an hexagonal geometry. The two important crystalline allotropic forms of sulfur are also there, such as rhombic sulfur, monoclinic sulfur, as well as there is, gamma sulfur, alpha sulfur, beta sulfur, as well as there's gamma sulfur, plastic sulfur, and number four is amorphous sulfur, uh, which is not mentioned in our book, but these are some uh, crystallines. Moreover, rhombic sulfur is a yellow octahedral crystalline form. It is stable at ordinary temperature when it is, below 95.5 centigrade, and if it is heated above 95.5 centigrade, it changes into monoclinic sulfur. Moreover, there is another concept which is known as transition temperature. When the temperature at which two allotropic forms of the same element are existed in equilibrium with each other, it is known as transition temperature. The transition temperature of rhombic and monoclinic sulfur is 95.5 centigrade. Below this temperature, there is rhombic sulfur. Above that temperature, there is monoclinic sulfur. Now, uh, at the 95.5 centigrade, there is an equilibrium formed between both the rhombic sulfur stage as well as monoclinic sulfur stage, due to which this temperature at which both states exist in equilibrium with each other is known as the transition temperature. Apart from which, when it comes to some types of crystalline solid, some types of crystalline solids are given below, um, such that if you talk about crystalline solids classified into four main categories, such that these are classified on the basis of their attractive forces as well as the arrangement of particles. Number one includes ionic solids. Ionic solids are those which consist of positive and negatively charged ions, and the bonding which is formed between them is known as ionic bond or electrovalent bond. The arrangement of these elements in three-dimensional network takes place in such a way that each ion is surrounded by a fixed number of oppositely charged ions, so that strong and long-range electrostatic attractions are developed among the ions in all directions, right? And apart from that, when it comes to their structure, the structure is crystalline. I mean, they do not exist in amorphous form, they exist in crystalline form. And some characteristics of ionic crystals are described as below, such that they are hard at room temperature due to the presence of strong electrostatic forces of attraction, and they are brittle and can be shattered easily by hammering. Reason behind it is that, uh, you know, whenever there is, if you are supposed to apply, let's take example of this. If we are supposed to apply, force over this crystalline structure, let's suppose this is sodium chloride, and when we are going to apply force over this crystalline structure, so uh, this force, if this force which is applied over crystalline structure is greater than the attractive forces, if this force applied is greater than the attractive forces which are holding these layers together, then then the force will cause to, break one layer of ionic solids with the other layer of the ionic solids, such that this layer and two different layers will be formed by applying force which is greater than the secondary forces of attraction which are holding the ionic solids together. As a result of which, when this bond is when this physical force of attraction is broken, it causes to, separate these layers, as it is in the case of sodium chloride. Moreover, they possess higher melting point, they are soluble in water and similar polar solvents, and they are unable to conduct electricity and heat in solid state, but in aqueous solution they are able to conduct electricity because their ions are able to move freely. Why in not in solid state? Because in solid state there is restricted vibration of ions about their allocated positions. Apart from which, when it comes to their factors affecting their shape, first and foremost is their ionic association. If their bonding is strong, if we are having oppositely charged ions closely packed in a specific order to form a particular shape, then at that moment the ionic association really matters. Such that if you are having the crystal of common salt, such as sodium chloride, each sodium ion is covered up with chlorine ion, and each chloride ion is surrounded by six sodium ion. This arrangement gives us a cubic shape. Moreover, when it comes to their radius ratio, radius ratio is a terminology which is given as a ratio between the radius of the cation to the ratio of anion, and that helps us to predict the shape of the ionic solid. Let's take example of the chart given below. Here, as you can see, if the radius ratio is between 0.15 to 0.22, then the coordination number would be 3. And here, the triangular due to the coordination number being 3, there would be a triangular shape formed. Example of this is given, such as for boron oxide. Moreover, when it comes to the radius ratio is 0.225 to 0.414, then at that point the coordination number is 4. Shape is tetrahedral. An example of this includes zinc sulfide. Moreover, when it comes to radius ratio, which is from 0.414 to 0.732, then the coordination number would be 6, shape would be octahedral, and sodium chloride will be formed. When there would be 0.732 to 1 as the radius ratio, coordination number will be 8 and cubic shape will be formed in case of cesium chloride. One more thing, sodium chloride also exhibits polymorphism. It exists in cubic shape as well as octahedral shape. Poor conductivity. Ionic solids are good conductors of electricity either in fused or in aqueous state due to the free movement of ions towards the respective electrodes when a potential difference is applied. However, ionic compound exhibit poor conductivity in solid state, which is detected dictate dictate which in indicates sorry which indicates that ions are not free to move. Rather, they stay in a fixed position, ensuring that the ionic crystal has a fixed shape. Moreover, when it comes to covalent solids, these are those atomic solids which consist of atoms of the same or different types, which are bonded to each other by strong covalent bond, such that a perfect single crystal of a covalent solid is considered as a single giant molecule, as seen in diamond and silicon carbide. And apart from that, it includes the covalent bond, and moreover the two types of structures are quite prominent in the covalent solid, which includes the giant structure which exhibits in diamond, and second includes the giant structure in diamond and silicon carbide. And apart from that, there is another structure which is formed a layered structure, which is known as the layered structure in graphite, and giant structure in diamond. And apart from that, in diamond, each carbon atom is covalently bonded to the other carbon atom at an angle of 109.5 to form basic tetrahedral unit. This trend of covalent bond formation continuously in the entire crystal three-dimensionally, and develop a network of covalent bonding which give rise to a giant structure. Moreover, the close packing of atoms and large number of covalent bonds. Diamond is the hardest substance known having a high melting point, right? And apart from that, graphite is bonded to three other carbon atoms at 120-degree angle, because it is exhibiting hexagonal shape, due to which it exhibits a bond degree as 120 degree, bond angle as 120-degree. Moreover, forming layers of hexagons. These layers are held together by weak van der Waals forces and are 3.35 angstrom apart from each other. The greasy nature of graphite is due to interlayer space, which allows one layer to glide over the other. Some characteristics of properties of covalent solids are described, that they possess high melting point and high density due to strong bonding among atoms, as well as they are bad conductors of electricity. They are insoluble in water. Graphite conducts electricity parallel to the layers, but uh, not conducts in perpendicular layers, because in parallel layers there's availability of delocalized electrons. Moreover, when it comes to metallic solids are made up of metal atoms, such that according to the electron C theory presented by a scientist, metal atoms lose their all valence electrons into the vacant space and become positively charged metal ions. These positively charged metal ions arrange themselves in a three-dimensional crystal lattice and bond with a sea of electrons. And this unique force of attraction between the metal atoms is known as the metallic bond formed between them. It is also a physical force of attraction. And that metallic bond is in atomic solids. Here, as you can see, this is a type of bond which is formed over here. The atoms lose their valence electron, due to which they form a sea of electron, and at that moment they form a bond, a physical force of attraction between the other atoms, between the electron and the atom, which is known as the metallic bond. Characteristics of these includes, first and foremost, that they are, they can be identified by their malleability and ductility, which means we can, convert them into wires by, thinning them, as well as we can, them into thin sheets. Moreover, when it comes to metallic solid, they look like dull, but when freshly cut, the inner layer appears shiny. This property is known as metallic luster. um, Reason behind it is that they appear shiny because now, it's a bit of, you know the topic which I would like to take apart from what we are studying here. As you can see, within the metal atoms, the electrons are taken aside. Let's suppose this is an electron, this is a positive metal ion. Now, when electron will tend to move in the electron sea, so at that moment it will tend to, have electrons. We know that these are highly energized particles, due to which they will now, tend to exhibit, due to their movement, they will tend to exhibit several quanta of particles, several quanta, such that, we have studied in the quantum theory in the previous chapters, that when electron moves from high energy state to low energy state, it releases quanta, and when moves from low energy state to high energy state, it go absorbs quanta, such that when we are going to cut the fresh layer, that fresh layer when cutted will cause to give us a layer which is, having uh which is having the electrons which are highly energized, due to which they exhibit the quanta, due to which they cause to exhibit, you know a shiny layer over them, which makes them appear quite shiny. So this is the reason behind it. And apart from that, when it comes to electrical conductivity of metallic solids is due to the free movement of delocalized electrons in electric field, as well as they are good conductors of electricity. uh, when a rod of metal is heated from one of its terminals, the free electrons of metal, absorb heat and move towards the other side due to increase in the kinetic energy, and thus free electrons then tend to move towards the other end of the road, which is relatively cooler. As a result of which, when they tend to move on the other hand of the road, where which is relatively cooler, the other end of the road, due to the arrival of several high kinetic energy particles, high kinetic energy electrons, cause to become heated as well, due to which the heat is then transferred due to the high kinetic energy electrons transferring from the hot region to the colder region, cooler region of the handle or the metallic solid. Moreover, when it comes to some other characteristics, we are going to discuss about uh, a few of the things which are important over here, such that here we are having, first and foremost, the covalent solids. Covalent solids, basically, these are those solids which are, sorry, metal, sorry, we are having molecular solids. Where is it? Molecular solids, these are bonded by physical forces of attraction, such that the constituent particles are made up of physical forces of attraction, such as dipole-dipole interaction, hydrogen bonding, or London forces, which are weak forces of attraction. Physical forces, which are weak forces. And these intermolecular forces are much weaker than attractive forces for covalent bond or ionic bond, or the other types of bonds, such as metallic bond. That is why molecular solids melt under relatively low temperature, and that is the reason the sublimation process occurs within the molecular solids. And they melt under relatively low temperature. With ionic or covalent solids, molecular solids have low density, as well as they have low melting point, and serve as bad conductors of electricity. Let's take the example of some comparative comparative covalent solids, sorry, comparative molecular solids with other uh, crystalline solids, such that they are having types of particles as molecules, as well as they are having the nature of bond is dipole dipole interaction, London force, hydrogen bond, or other type of physical force of attraction. When it comes to their crystalline general properties, they are having soft, low melting point, and they are bad conductors of electricity. Example of this includes ice, iodine, dry ice are all examples of this. But it doesn't really mean that they are not having any sort of crystal um 3D geometry. They are not having any sort of 3D geometry. That's not the point at all, because they are having a 3D geometry, as these are types of crystalline solids. When it comes to crystal lattice, it is a very important topic here, that atom, ions, or molecules in all solids are already packed on fixed positions and in the most adequate manner. Now, crystal lattice here is a three-dimensional structural arrangement of the particles of the crystalline solid, such that a single crystal lattice can be assumed as a college, and within that college we are having a proper definite geometrical arrangement of different classes, and each class is basically having different chairs inside it, so that each class which would be having different chairs inside it would be known as the basic unit of the college. So in that case, the basic unit similarly for crystal lattice would be considered as a unit cell. Let's take the example here. Here, as you can see, the smallest structural part of a crystal lattice is known as unit cell. It shows a 3D pattern of specific crystal lattice in a least volume and provides us a detailed structural information of a crystal solid, such that the small repeating pattern from which the lattice is built is known as unit cell. It continually repeats itself within the lattice structure and ultimately forms a crystal lattice. And if we are able to study the structure of the unit cell itself, we are then able to conclude and decipher the entire crystal lattice as a whole. So in that case, it is a very useful part, and there are certain parameters which we utilize in order to study the crystal lattice unit cell, which are known as the which are certain parameters over here, which are known as crystal parameters, lattice parameters, unit cell parameters, which are known as these are six parameters. Three of them are the length, and three of them are the angles. Now, lengths are indicated by ABC and angles are represented by alpha, beta, gamma. When it comes to angle between B and C, angle between B and C would be alpha, angle between A and B is gamma, and angle between A and C is beta. So this is what we what it is about. And when it comes to some other part, we are also having a type of crystal system in which we classify different crystals. So classification is done in such a manner that there are seven crystals. Number one crystal is cubic crystal, tetragonal crystal, after which there is orthorhombic, after which there is rhombohedral, after which there is hexagonal, and then monoclinic and triclinic. So within these crystal system, uh, we are having different types of crystals. A common MCQ's point that in which type of crystal system all types of cubic cells are present. In cubics in the cube in all types of cells are present, such that in which crystal cell system there is face centered cubic, as well as edge centered cubic, as well as body centered cubic, as well as uh you know body centered cubic present. So in this case, the cell in which all of the cells are present is known as a cubic cell, and the cell in which sorry the cell in which all types of cubic cells are present is known as orthorhombic, and the cell in which three of these cells are present, it is known as cubic, and in which only one cell is present, which is known as the body centered cubic, is known as triclinic, hexagonal, as well as there is rhombohedral, and fourth one includes And fourth, these are the three shapes in which only body centered cubic is present. So these are some characteristics. Rest when it comes to monoclinic. In monoclinic, we are having two shapes, such as we are having, we are having face centered and we are having body centered, but we are not having cube age centered. When it comes to orthorhombic and tetragonal, in case of orthorhombic and tetragonal, orthorhombic having all four shapes, and tetragonal is only having, again, it is also having two shapes, just like monoclinic. And triclinic is having only one shape. Now, when it comes to their angles, the angle is arranged in such a manner that we can also use some mnemonics in order to, learn these. In the next video, we are going to have, a separate mnemonic class in which we are going to discuss how to, memorize these, not memorize, but actually, get some sort of trick or strategy in which we can memorize these crystal lattice. And these crystal lattice basically give shape to, 14 different lattices. These seven crystal system give to 14 different shapes of the crystal, which are classified in the Bravais lattice, which are known as Bravais lattice. These are seven shapes which give rise to, uh, different cubic cells, which in 14 cubic cells, which is known as Bravais lattice, which was discovered by the scientist known as Bravais, right? And the bond angles are also mentioned here. We are going to have another video in which we will discuss about all the mnemonics, in which we have, for chapter number 6, solids, right? And when it comes to the unit cell of sodium chloride crystal, sodium chloride is one of the most common ionic compound. The shape of unit cell of sodium chloride is face centered cubic, in which each sodium ion is surrounded by 6 chloride ion, and each chloride ion is surrounded by 6 sodium ions. The formula of sodium chloride is sodium NaCl, and it can be determined by, total number of sodium and chloride ions in the each atom. Now, chloride ion determination is in such a manner: there are 8 chloride ions at the 8 corner of cubic cube, while 6 chloride ions at the center of the 6 faces. So as there are 8 chloride ions at, 8 corners of the cube, so uh, let me just try to draw the structure. Let's suppose this is one cube. Likewise, such that now the structure is drawn, and here as you can see, now, uh, if we talk about the arrangement of, first and foremost, we are discussing the arrangement of chloride ions. So arrangement of chloride ions can be arranged in such a manner that here, as you can see, each corner at each corner, as there are 8 corners, at 8 corners of each cubic cell. If this is one cubic cell, now one cubic cell, at one cubic cells each corner there would be 8 uh, chloride ions. Let's suppose at all corners there are 8 chloride ions, and here, let's suppose we are having 8 chloride ions, 8 chloride ions. And at the same moment, when there are 8 chloride ions, the number of corners which are sharing this one chloride ion with their, corners are around 8. Now you'd be asking how. See, as you can, now this is a one cubic cell. It is having one of its, uh, this corner, one at this corner. This is the corner of one cubic cell 1, second cubic cell of this cubic cell 2, another cubic cell from this side 3, another cubic cell from this side 4, and another cubic cells corner this side 5. From because these are the four corners on the front side. On front side we have got four corners. Now on the other hand side, when we are going to draw its structure further, on the back side there will also be some sort of arrangement. So that let me just try to let me just try if I can, right? And if I'm supposed to, let's suppose, if I'm going to put a similar structure behind it, if I'm going to put a similar structure behind it, so at that moment there will be, you know that same corner. Let's suppose this is the same corner over here. So now that same corner will be having one corner of this cubic cell, one corner of this cubic cell, one corner from front, one corner from behind, four corners on this side, and four corners of the other cubic cell from this side, from this side, from that cubic cell, that cubic cell, and that cubic cell, which means eight corners will share one single chloride atom. So we can say the number of chloride atoms are 8, and each chloride atom shares 1 upon 8 of the chloride atom. If each corner is, 8 corners are having one chloride atom, due to which we can say that here the number of chloride atoms share with each side would be 1 upon 8. So when we are going to cancel it out, we will get the answer as 1, which means one chloride atom is present within the geometrical arrangement in a single unit cell. Similarly, if we talk about phase center, in phase center, first let me just clear it out that on face, on the edges we are having 12 atoms, on face we are having 6 atoms, and on corners we are having 8 atoms. So these are some common things which you need to consider about. and and when it comes to body centered cubic will be basically having chloride atom, um, in body centered cubic there will be the atom which would be at the center of the body, which means at the center of symmetry there will be one atom, right? This is how we'll classify it. Now when it comes to face centered cubic, now on the other hand side, six faces possess chloride ions at the center, but each face possess two unit cells. Therefore we can say that there are six chloride ions, right? Six chloride ions, and each chloride ion, six chloride ions are there, right? And each chloride ion is shared by two of the faces. How? Let's see. If we talk about, uh, let's suppose if we talk about this face, this is a face, right? It's an entire face. Now that entire face will be having, there's six chloride atoms on the faces, such that if there is one atom on this face, then this face will be, sharing this single atom with the other face which is with it, such that this cube's face is this. Let's suppose this is denoted by this color, uh, a green color, and here this is a similar face in the 3D structure which is denoted by purple color. Now these two faces which are joined together by a single chloride atom will be sharing half of the chloride atom, which means the share of chloride atom to each face would be 1 upon 2, right? So when we are going to take uh, the calculation that each phase will be having 1 upon 2 of the chloride atom, and there are 6 chloride atom for the 6 phases, so at that moment we can simply calculate in such a manner that due to half chloride atom share, and on the other hand side the number of phases which are present in the cube are 6, due to which 6 would be divided by it, due to which number of chloride atoms given would be 3. Chloride atom given would be 3. So at that moment, we have concluded that there would be 3 plus 1, 4 chloride ions present within the structure. Moreover, when it comes to sodium ion structure, one sodium ion, basically sodium ion exists in BCC, body centered cubic, as well as ECC, edge centered cubic. Moreover, when it comes to chloride ion, it exists in corner centered cubic, CCC, and face centered cubic, FCC. These are some important MCQs point. Apart from which, when it comes to sodium ion, when it comes to body centered cubic, we know that body centered cubic is only having one atom in the center, one ion or one atom or one particle in the center. Whereas on the other hand side, when it comes to the edge centered cubic can be classified in such a manner that there are 12 edges, right? And if we talk about the number of atoms on one hand side, number of atoms on one hand side, let's suppose this is a structure. Let me just try to draw over here again. So here, as you can see, if we talk about uh, the edges, there are 12 edges, right? And on each edge, if we are supposed to put one atom on each edge, if there is an atom present on this edge, so at that moment when the atom would be present on the edge, that atom would be shared by four edges. Now you'd be wondering how four edges. Let's see. One edge of this cube, one edge would be of this front one cube, one edge of this second front one cube, and one edge of this cube from the three-dimensional view, and one edge of this cube. These four edges which are not properly shown within this diagram. So when these four edges are, sharing one chloride atom, we can say that each edge would be having 1 upon 4 of the chloride atom. So 1 upon 4 of the chloride atom being shared will be multiplied by the 12 edges, due to which the answer which we'll get would be 3, which means 3 sodium atoms are present. Sorry, it was not chloride but sodium ions. So it means that there are 3 sodium ions on the edge and 1 sodium ion on the center or body center, due to which it would be considered as 3 plus 1 4 as the total number of sodium ions in each unit cell. Now when we are going to take the ratio of sodium cation to anion, we'll get our answer as 1, due to which we can say, due to its ratio is 1, it is having a shape which is known as the cubic shape. And at that moment, this is how we gain its atomic ratio as well. And this is a lattice structure present within it. When it comes to close packing in metallic solids, close packing in metallic solids, is another topic in which we are going to discuss about you know arrangement of the metallic solids in layered form, such that metal atoms are arranged most likely in a tightly packed balls, which minimizes the empty space between them and justifying their high density. The three types of close packing found in metal. First includes the hexagonal close packing. In this type of close packing, the empty spaces are created due to three neighboring first layer is filled by the alignment of the spheres of the second layer, and the spheres of the third layer directly parallel on the sphere of the first layer, so that an ABA type arrangement is developed, which covers that 74% of empty space, which covers 74% of the empty space. As you can see, if there is one layer, then one layer will be parallel to the second layer space. So let me just explain it here. So here, if there's one layer, and that one layer is having tiny spaces in between them, these are the tiny spaces between that single layer. Now uh, in order to cover these tiny spaces, we can have another layer which can cover these tiny spaces. Now, if the tiny spaces of the first layer is covered by the second layer, then there would be tiny spaces created by the second layer. Now, in order to cover the tiny spaces of the second layer, we will be putting a third layer. That third layer will be covering the tiny spaces of the second layer, but again it will produce tiny spaces same as that of first layer, which means it will be parallel to first layer. So at that moment, that would be a layer which would be parallel to first layer, and that arrangement will cause to produce 74% of the empty space. Another type of structure which is explained over here is about face-centered cubic close packing, such that if the voids among the spheres of first layer are filled by spheres of the second layer, however the spheres of third layer are displaced horizontally from the first layer, this gives an ABCA arrangement, such that if there is first layer, after which there is second layer, third layer, and the fourth layer would be same or parallel, or horizontally displaced from the first layer, which covers 74% of the empty space. Now these are mathematically derived. Actually, there is a complete derivation on how to find the packaging space, but according to our book we are only given this statement. So as you can see, this would be the fourth layer, and the first layer would be having would be horizontally displaced. The fourth layer would be horizontally displaced from the first layer. Body centered cubic is the one in which there are relatively bigger voids, such that it covers only 60% of the empty space, and arrangement of layer is ABAC type. Moreover, hexagonal close packing and face center cubic close and body center cubic close packing, uh, you know, uh, data is given, the summary is given, and the coordination numbers are important, which are given as well. Here, hexagonal close packing having 12 coordination number, face centered cubic having 12 coordination number, and body centered cubic having 8 coordination number. Now, when it comes to lattice energy, it is already discussed, but let us repeat it once again. That here, during this process, a high amount of energy is released whenever we are having two gaseous ions. When two gaseous ions are brought closer to each other, and they combine with each other in order to form a three-dimensional structure in a certain pattern, then at this moment a high amount of energy is released, which is known as lattice energy, which is denoted by delta H LE. As we have previously discussed in the Hess law, as well as in the Born-Haber cycle, such that it is the energy which is associated with electrostatic interaction between the ions in a crystal, and it can be defined as the quantity of energy which is released when 1 mole of the ionic crystal is formed between the metallic ions, right? So amount of energy which is released when 1 mole of ionic crystals are formed from its gaseous ions, then it is known as the lattice energy. And the amount of energy which is required to break 1 mole of crystalline solids into isolated ions in the gaseous phase is also known as the lattice energy. But in order to explain it in terms of Born-Haber cycle, we take it as combination of the sodium and chloride ions in order to form sodium chloride, and it is expressed in kilojoule per mole. If it is in terms of releasing energy by the combination of the gaseous ions, then it would be negative. It would be indicated by a negative sign due to exothermic process, and it would be broken down. If the sodium chloride is decomposed into sodium and chloride ions using the gain of energy in an endothermic process, there would be a positive sign. Moreover, when it comes to some other characteristics, the reason for uh, this is that it is already discussed, and the lattice energy decreases with the increase in the size of cations or anions, such that the smaller size of cation or anion, the closer packing of oppositely charged ions, and it will require high energy to break the lattice, convert the solid into isolated ions. For example, if the lattice energy of sodium fluoride is 923 kilojoule per mole, which is higher than potassium fluoride 821 kilojoule per mole, because of smaller ionic radii of sodium than potassium, as a result of which, due to smaller ionic radii, there will be high nuclear force, due to which there will be more, due to smaller ionic radii, there will be high nuclear force of the sodium as compared to potassium, as a result of which it will be more, you know, able to release more amount of energy. Let me just explain it on another paper. If you're having sodium, right? Sodium is having a sodium ion. Let's suppose sodium ion having how many number of electrons? 10 electrons, because it is in the ionic form. One of its electron is lost, right? 10 electrons are there, and due to the release of 10 electrons, its atomic radii is smaller as compared to potassium, because potassium ion basically is down towards sodium in the groupic arrangement, such that sodium ion is having smaller radii and it is having higher radii, due to which the atomic radii of potassium is higher, sodium is less, due to which we can say the of potassium is nuclear force of potassium is smaller because of higher atomic radii, and nuclear force of sodium is high due to high atomic radii. Due to smaller atomic radii, the sodium is having high nuclear force, and due to smaller nuclear force in potassium can be easily, released into its gaseous signs, as well as can easily form salts from its gaseous signs, or easily form ionic crystals from its gaseous signs, due to which we can say that due to less amount of nuclear force, there's less amount of lattice energy in formation and decomposition of potassium crystal, and due to high amount of nuclear force in sodium, there will be high amount of lattice energy required in order to decompose as well as form the ionic crystal of sodium. So in this case, this is the reason for this, and examples are given such as sodium fluoride having 923 kilojoule per mole and potassium fluoride 821 kilojoule per mole. Moreover, when it comes to other characteristics, lattice energy is also affected by the charge on ions, such that the greater the charge on ion, the higher is the lattice energy. For example, lattice energy of beryllium fluoride is 33,500 5 kilojoule per mole, which is much higher than lithium fluoride, because lithium possesses a single positive charge, and beryllium is having a higher valency, due to which it is having higher charge. And here this is a summary of a few lattice energies of different compounds. And apart from that, lattice energy are important in predicting the solubility of ionic solids in water. Ionic compounds with smaller lattice energy have greater hydration energy and are more soluble in water, and it is indirectly determined by the bond harbor cycle, and it is the one thing which we have previously discussed in our previous videos as well. And here one more reason is how does the hydration energy or dissolvability or solubility increases with the decrease in lattice energy. If there is decrease in lattice energy, then it simply means that decrease in lattice energy refers to weaker bonds formation. As there is weaker bond formation, you know as there's a decrease in lattice energy, it simply means there is weaker bond formation, which means in order to form uh, it if there's less lattice energy, then there will be less amount of energy which is required to break the ions, due to which there will be you know an inverse relation formed between the hydration energy and lattice energy, such as if the lattice energy is less, there will be less amount of energy to break the ions, which means it would be easier to dissolve that particular crystal into that into the water, due to which its hydration energy will be increased, as a result of which hydration energy is inversely proportional to lattice energy, such that lattice energy is increased, hydration energy is decreased, because lattice energy increase you know causes to make it more difficult for that ionic crystal to dissolve or dissolute itself into the ions, due to which it has less hydration energy, due to which there will be less solubility. So this is how we uh, conclude it, and hopefully we'll meet again in another video.